Hi, welcome back to a new lecture from Computer Vision from Scratch. Today we'll be looking at MobileNet and how it enabled deep learning models to be really small so that you can operate it even in handheld devices like mobile phones or IoT devices. So before we look at MobileNet architecture and before we implement it, we'll also have a brief recap of what we have tried so far and how those models have worked on the dataset that we have been looking at. So with that, welcome to the lecture. So the value proposition by MobileNet is self-explanatory in the word MobileNet itself. It's a neural network that can fit in your handheld devices like mobile. And the need for this came naturally. So when deep learning scientists were working on deeper and deeper neural networks, it inevitably resulted in big models such as 138 million parameter models like VGG, which had 512 megabyte storage space. So it was very difficult to operate, store and infer from small devices like Raspberry Pi or mobile phones, but their accuracy was very high. Then people introduced Inception V1, that was also a much smaller model with really good performance. And then ResNet 50 came, which was not a very small model, but its performance was really, really good. So all these things were happening starting from AlexNet in 2012 all the way till 2016, 2017. But the problem was, as I mentioned, consumption of memory was very high. Bigger models required more storage space. Inference time, meaning if you want to run the model, the trained model to infer on a new test dataset, the time was a bit longer. What this means is for real-time applications, which may be required on small devices, it's very difficult to implement these models like VGG, AlexNet, ResNet, etc. And this will also result in huge battery drain in small devices, which is not the ideal way to design convolutional neural network models for real-time computer vision tasks if you want to operate them on small devices. So we needed lightweight architecture, but we already know what's the issue with lightweight architecture. The problem is their accuracy might not be so good. So the initial goal of researchers was to find an architecture which was reasonably small with a decent accuracy. That was the original goal. And today we'll see what MobileNet achieved in 2017. It's not so long ago, right? So this is still a relatively recent model, but we'll see what it has achieved and why it has risen so much in popularity. So MobileNet was introduced or proposed by Google in 2017. The paper, which was published on Archive, currently has 32,000 plus citations. It's a huge number. And this is really, this shows the legendary status of this paper. The title of the paper was MobileNet's Efficient Convolutional Neural Networks for Mobile Vision Applications. So the value proposition was so direct in the paper title itself. And there were multiple authors. So this is from one of the authors of the paper. I just took this screenshot from his Google Scholar. So now, before we look at what exactly did MobileNet do specifically to attain an architecture that reduces the size, that relatively increase the efficiency for such a small model, let's recap a little bit and let's see what we have been doing so far in the course, just in case you are watching this lecture after some time, if you have forgotten what has happened in this course so far. If you are already familiar with what exactly has been happening, feel free to skip to the next section after the recap. So what we did was we started with the 5 flowers dataset: daisy, dandelion, roses, sunflowers, and tulips. We had 1,000 images in each class. So it was like a 5-class classification problem. We thought of starting with a very simple architecture. So we started not with a neural network, but with a linear model. So the RGB 3-channel image was converted into a flattened layer, which was connected to a fully connected set of 5 nodes in the output layer. We did not use any activation function here, but in the final layer, we had a softmax activation to convert the output numbers into a probability distribution. The accuracy of this model was 40 to 45%, and this was training accuracy. The validation accuracy was 35 to 40%, not so good. The random classification accuracy for a 5-class classification using the worst models can even lead up to 20% accuracy. The loss in this case was 10 to 20. And then we thought, okay, we might need more hidden layers. So we started with 128 hidden layer node architecture with ReLU activation function. This resulted in similar accuracy, which was a bit disappointing. We had 40 to 45% training accuracy, but the loss was one order of magnitude lesser. It was 1 to 2. This was very surprising because if loss decreases by an order of magnitude, how come accuracy does not change? This was because each individual predictions were being made at the same accuracy, but the confidence of predictions increased. So if this is the true label, and if in one case you have this kind of prediction and in another case you have this kind of prediction, obviously this second type of prediction is more confident because the values are closer to the class 0. So this is what was happening in the hidden layer model. Then we thought maybe there is overfitting happening. So let's try to eliminate overfitting. Why did we assume this? Because we were seeing that the training accuracy was generally 10% higher than validation accuracy. Then we decided to implement some regularization techniques. So we had batch normalization, dropout, and early stopping. Early stopping was not really necessary, but we implemented it anyway for the future iterations with more number of epochs. And this actually resulted in validation accuracy up to 50-60%. This was very good because in this particular case, we even achieved training accuracies of 65-70% also. So we were happy, but not fully happy because we were expecting like 90-95% accuracy, but 50-60% is what we had. That is when we truly realized that we have to do transfer learning. We should not be training from scratch. We should use pre-trained weights. So we implemented transfer learning with ResNet 50 architecture, but it was with very minimal hyperparameter tuning. We did not do much to optimize the hyperparameters. We obtained 100% training accuracy and 80% validation accuracy. Quite good compared to the previous results, but training being 100% and validation being 80%, clearly there is overfitting happening. But our goal was to experiment with various convolutional neural network models rather than completely hyperparameter optimize one model and see if we can push it to the limit. That was not our goal. So we decided, okay, let's start with the earliest of CNNs, and then let's go chronologically with more and more advanced CNNs in the future lectures, right? So we started with AlexNet, the famous neural network architecture, which radically changed the way deep learning was implemented for computer vision. This was introduced in 2012 by Alex, Professor Geoffrey Hinton, who won the Nobel Prize in Physics 2024, and Ilya Sutskever, who was the co-founder of OpenAI. The validation accuracy was 90% in this case, and training was 95% for just 10 epochs. Very good results. We were extremely happy at the end of this. Then we moved ahead with another neural network, VGG16. So this was introduced at Oxford University. We tried 50 epochs, and surprisingly, we had 85% validation and 75% training. So clearly, there is no overfitting, but it was more like undertraining or underfitting was happening. Then we switched to GoogleNet, which was later renamed as Inception V1. And we again ran for 50 epochs. So please note, the moment we switched to 50 epochs is the reason why we switched to 50 epochs is because we noticed that for 10 epochs, the accuracy was not so high compared to the previous models. And the time when we started looking at AlexNet, pre-trained AlexNet model, we switched from TensorFlow Keras to PyTorch. So that was one change that happened from this lecture to the lecture where we looked at AlexNet. Then we continued looking at PyTorch libraries for pre-trained models. Then after Inception V1, we moved to SqueezeNet, which gave very good training and validation accuracy, 91 and 95% respectively. I mean, for validation 91, training 95. For 50 epochs, we were very happy because SqueezeNet model was very small. It had only 1.2 million parameters. So it's a very simple, small model, unlike VGG, which had 138 million parameters. Then we moved to the completely radically new framework, ResNet 50. Although we had implemented ResNet 50 in one of the earlier lectures, we did not go through the architecture of ResNet in that much detail. But in the previous lecture, we went through the detailed architecture of skip connections, the residual learning, etc., which was happening in ResNet. And this architecture is truly fascinating. The paper has a big legendary status with 270,000 citations. Number of epochs were 50. Training accuracy 97% and validation accuracy 93%. And by far, this is the best model that we have seen in this course. And this is something that we discussed in one of the earliest lectures also. When we got very poor accuracy, we were really looking forward to having models that will give us 95-99% accuracy. And this ResNet 50 with minimum hyperparameter tuning, we did not place too much with hyperparameters, but still we have reasonably good training and validation accuracy that really makes me happy. So now with this, we can get into the reason why MobileNet was introduced, what exactly was the innovation in the MobileNet, did it win some competitions, and what's the whole architecture that was used in the MobileNet V1. And we will also implement MobileNet V1 for the 5 flowers dataset, and let's compare the accuracy against all these accuracies that we have been obtaining so far. All right, so with that, let's just get into what we are about to do today. And before we start, let me take a moment to remind you why we all started learning computer vision, because we are very serious about this topic. So as I always mention, since you have started this with a reason, you must finish this, and let's all take a pledge together that since we have started this with all seriousness, we are going to finish this. And if you want to keep yourself accountable, feel free to comment publicly or keep each other accountable if you have a friend with whom you would like to learn computer vision. So now coming back to MobileNet, the core idea of MobileNet was depthwise separable convolution. So instead of implementing a very expensive convolutional computation, like for example, let's say we have an image at the input which got transformed into like a 32 input channel. And if to this 32 input channel, if we want to apply a 3x3 filter such that we have 64 output channels at the end of the convolution, then we will require, after training, how many parameters? A 3x3 filter will have 9 parameters. Like that, there are 32 input channels. So you have to multiply 9 by 32. And there are 64 output channels to which we are projecting the data. So we have 9 multiplied by 32 multiplied by 64, 18,432 parameters. This is the number of parameters that we will need if we are applying a standard convolution to a 32 input channel image, right? Now, the image itself can have different dimension in X and Y, but that we are not mentioning here. Here, by parameters, we are simply mentioning the total number of learnable parameters, which are part of the convolution filters. Now, what does MobileNet V1 do differently? So what the researchers who proposed MobileNet figured out is that instead of applying one gigantic convolution like this, we can split the convolution operation into 2 steps. First, apply a depthwise convolution and then apply a pointwise convolution. I'll show you exactly what this means. So let's say we have a depthwise convolution as the step 1, right? So just look at this left part, which is the depthwise convolution as step 1. Step 2 is pointwise convolution. So here what is happening is, let's say we have 32 channels like this. Okay. The image size can be anything. Image size can be 224 by 224, whatever it is. Like the not image, the input data. It's a representation of the image. It's not actually image necessarily. Now, this can be whatever, 224 by 224, 64 by 64, whatever it is, but there are 32 channels. Now, to each of these 32 channels, we are applying one separate convolution of dimension 3 by 3. So this is 3 by 3, this is 3 by 3, this is 3 by 3. 3 by 3 is just an example. It can be whatever. So total number of learnable parameters would be, since we are applying this convolution separately to each channel, we have 3 by 3 plus 3 by 3 plus 3 by 3. Like that, we have to add it 32 times. So we have to add 9 32 times. So the total number of parameters in this depthwise convolution part will be 288. And why do we call it as depthwise convolution? Because just look at the number of channels. So each feature in separate layers are learned separately, because we are not applying convolution such that the features in different layers are getting mixed. That is not happening. That the different layers, meaning different channels, which is like the depth feature, it is kept intact. We are not mixing the features in different channels into one single concatenated channel. That's not happening, right? So after we do this, then yes, we concatenate it back into 32 channels. So this will also have 32 channels. So input has 32 channels, output here has 32 channels after the depthwise convolution. And this means total number of learnable parameters for this example that we took is 288. Then what do? We apply something called as pointwise convolution. In this pointwise convolution, we simultaneously look at one single point, meaning one single pixel throughout the different channels. So if we have 32 channels, we look at one pixel in the entire depth of 32 channels, right? But now our output may have a different number of channels. So instead of having 32 channels, our output, let's say, it may have 64 channels. It may have 128 channels, depending on what we want. So we have a one-by-one convolution applied through 32 channels at the same time to produce one number, right? So that will be how many number of learnable parameters? We will need 1 by 1 by 32, that many number of learnable parameters. But we are applying this such that we are creating 64 channels in the output. So for producing each channel output, we will need a separate filter, which means this number we have to add 1 times 1 times 32, which is 32. We will need 64 times. So multiply this by 64. So this number turns out to be what? 2048. 32 multiplied by 64. So in the initial depthwise convolution part, which is the step 1, total number of learnable parameters are 288. Then in the pointwise convolution part, which looks at the entire depth simultaneously, entire 32 channel depth simultaneously, there are 2048 learnable parameters. The 64 output, the desired output of 64 channel is just some example that we are taking. This 64 can be 12, whatever we desire. But then we also have to have an apples to apple comparison. We have to change here also, this 64 also we'll have to change to 12, because we said that output channels number is 64. But if we wanted 12, then 3 by 3 by 32 by 64 by 12. So that will be the total number of parameters instead of 18,400. But here, to have a fair comparison, let's keep the dimensions the same. Input will have 32, final output will have 64. So here, total number of learnable parameters is the sum of these two numbers, which is 2,336. So now, what does this mean? Instead of 18,432, you just need 2,336 parameters, which is almost like an order of magnitude reduction, right? 9x fewer parameters. And apparently, this results in very less accuracy loss, which is a great thing. So this was the innovation behind MobileNet. So they introduced this idea of performing depthwise convolution and then pointwise convolution. So this way, you can learn features in different channels separately in the depthwise convolution part. And then in the pointwise convolution, you are combining the information across the channels to get some channel-wise information condensed into one single number. And the overall architecture of the MobileNet V1 was like this. So the starting image input is 224 by 224 by 3. And they are trying to perform a 1024 class classification. But in our case, we will obviously be changing the last layer into a 5-node layer because we are performing 5-class classification. But otherwise, just look at this individual module. So this depthwise separable convolutions, ds-con, then this is ds-con, this is ds-convolution, depthwise separable convolution, depthwise separable convolution. And in each of these, there is depthwise convolution and pointwise convolution. So once we perform the depthwise convolution, we perform batch normalization and then apply activation, ReLU activation function. Here in pointwise convolution, after the pointwise convolution, we apply batch normalization and we apply ReLU activation. And this DS convolution block is repeated multiple times to build the entire MobileNet V1 architecture. Fairly simple architecture if you compare this against, let's say, GoogleNet Inception V1, which had a bit more complicated looking architecture, but this is a bit more straightforward. We can also do a comparison of what the architecture dimensions, I mean the megabyte size, performance, etc., was compared to all the other architectures that we have looked at in this course so far. So here, this table is a comparison between these models: AlexNet, VGG16, Inception V1, aka GoogleNet, SqueezeNet, ResNet 50, MobileNet V1, right? All the models that we have looked at in this course so far. AlexNet was introduced in 2012, the very first legendary deep learning model for CNN model. VGG16 was the second prize winner in ImageNet competition in 2014. Inception V1 won the first prize in 2014. SqueezeNet did not win any prize in 2016, but it was a very efficient model that could reduce the number of parameters. ResNet 50 in 2015 also won the ImageNet competition. So this was the next legendary neural network CNN architecture. And then in 2017, MobileNet V1 came. AlexNet was introduced at University of Toronto, VGG16 at Oxford, VGG Group, so Visual Geometry Group, Inception V1 by Google, SqueezeNet by UC Berkeley plus DeepScale, ResNet 50 by Microsoft, and again MobileNet V1 by Google. The core idea of AlexNet, as we have discussed in this course, is they introduced deep learning idea for image purposes for one of the very first times. And they also showed that you can perform parallel computing using GPU. They introduced a ReLU, dropout, etc., everything in one model to get a much better performance than any other model could do until that point. VGG16 showed that you just needed 3x3 convolutions and stack it across different depths. And unlike AlexNet, this was much simpler in terms of the convolution filters, but it had more number of layers. Inception V1 showed that instead of blindly doing 3x3 convolution, you can do multi-scale parallel filters. So they had 1x1 filters, 3x3 filters, and 5x5 filters. And some operations were happening in parallel. And why is it called multi-scale? Because 1x1 can look at 1 pixel at a time. 5x5 will look at 25 pixels at a time. So you can look at local features as well as a big global features. In SqueezeNet, there was parameter compression using 1x1. And then there was expansion, compression followed by expansion. In ResNet, they had skip connections and then that could eliminate the problem of vanishing gradients. So in the ResNet, they were trying to teach the neural network the residual, meaning the difference between output and input rather than directly predicting the output. And in MobileNet V1, which we are looking at in this lecture, we are looking at depthwise separable convolutions. So we have depthwise separable convolution and then pointwise convolution. The model depth, AlexNet 8 layers, VGG16 16 layers, as the name suggests. Inception V1 22 layers, SqueezeNet 18 layers with 8 fire modules. So in the Inception V1, there was inception module. In SqueezeNet, there was this fire module, which was repeating. In ResNet 50, there was the residual connection block, and the total number of layers were 50, as the name suggests. And MobileNet V1, it has 28 layers. But now comes the big idea, number of parameters. AlexNet had 60 million, VGG16 had 138 million. So this was the biggest and the one that took the maximum amount of time for us to train. GoogleNet had only 6.8 million. This was very efficient. SqueezeNet was even more efficient, just 1.2 million. ResNet 50 had 25.6 million and the MobileNet has 4.2 million. So for this MobileNet is really, really good. It's not as small as SqueezeNet, but it is the second smallest that we have looked at so far. And look at the model size. VGG16 is gigantic with 528 megabytes, whereas SqueezeNet is very small, 4.8 MB, and MobileNet is also very small, 16 megabytes. Now, we were mostly looking at top 5% accuracy in the ImageNet competition. So the best was ResNet with 93.6. SqueezeNet was not so good. And ImageNet is actually decent. It's close to 90%, which is fairly good. AlexNet was also not so good. So the main value proposition of SqueezeNet was AlexNet-like accuracy with a very small model. Then computation cost, if you look at this, SqueezeNet very low, ImageNet low. Rest of the ones have a high computation cost. And if you look at the inference speed, the fastest is MobileNet. Slowest is the VGG. And yeah, pretty much that's it. Deployed on GPU or server, whereas the MobileNet can be deployed on phones or edge TPUs. SqueezeNet can also be deployed on IoT devices or Raspberry Pi. So SqueezeNet and MobileNet has similar goals to make the model smaller so that you can perform edge computing or edge CNN tasks. Now let's look at the code. So I have implemented the entire MobileNet code in the code base that we have been following so far. And I have already obtained the classification accuracy, which I'm going to show you. But let me show you the relevant parts in the code where I have made changes. In the weights and biases project name, I changed the project name to MobileNet Flowers. In the architecture, I just named it as MobileNet. This is just for reference. We are not using this particular variable anywhere. And in the pre-training part, in the pre-trained model loading part, we import MobileNet _ v2 weights. So here, when I was importing, I used v2 weights. I could have also used v1 weights, but doesn't matter. Pretty much architecture remains mostly the same. And here I import mobile models equal to MobileNet underscore v2. And rest of the code remains pretty much the same. And I just want to show you the results that we have. So surprisingly, we have 90 to 91% training accuracy and 89 to 90% validation accuracy. I might also try MobileNet v1 on the side, and I will update the accuracy somewhere in this lecture notes. But feel free to try MobileNet v1 also. The only reason why I tried MobileNet v2 initially was I started running the code, and in the midway, I realized that I was running MobileNet v2, and then I did not bother to stop the code and change it to v1 because the concept remains pretty much the same. But I highly encourage you to try running the code with MobileNet v1. All right. But this is very good accuracy, right? For such a small model, we have 90-91% accuracy in training, 89-90% in validation. Fairly good. Conclusion is that for the size of this model, which is very small, the results are absolutely fantastic. I'll show you the code as well in the Google Colab notebook. So let me open that. So here is the Google Colab notebook. I'll share the notebook with you. First, I connect with Google Drive where my dataset is there. Then I import the necessary libraries. Then here is the weights and biases config. And when you run this part of the code, it asks for the weights and biases API. So you can copy paste that from the weights and biases website from your account. And then the routine data normalization or pre-processing. And the only part where your code will differ is in the training and validation directory path. So you can copy the Google Drive folder from my link, and then you can create similar path for wherever you are storing the dataset. And then that's it. Then you download or import the pre-trained MobileNet weights, whether it's v1 or v2. And then you train over here, define cross entropy loss and perform the training. And then you run the this function, train model function, and then you have the epochs results. So this is logged into the weights and biases platform, and from there only I got this plot. So I'm very happy because this training and validation accuracy is something that I would not have expected at the starting of the course for small models like this, because AlexNet had very good accuracy, but before that we were really struggling to get good accuracy, right? So now we are very happy. We are at a very good place, and we have explored so many number of CNN architectures. We have understood fairly well the history of how CNNs evolved, why certain models were introduced. It's not random, right? It's all for specific purposes. I'm sure people have tried trial and error for a lot of times, but they were smart in figuring out what might work and what might not. And that's the reason why people introduced the residual connections in ResNet. That could be the reason why people thought, okay, instead of just 3x3 convolutions in BGG, maybe we can try parallelly 1x1 and 3x3 convolutions or 5x5 convolutions like in the ImageNet v1. Or even in the VGG, they realized that unlike AlexNet, we can simply stick with 3x3 convolutions and just go with depth. So all these things work for different reasons. And I'm sure that accuracy will vary based on the data set. But with our data set, this is what we have got. So with that, we can wind up today's lecture. And I congratulate you once again for finishing yet another lecture. We are almost close to halfway of the course, I would say. And there are many more interesting concepts to cover in the subsequent lectures. I'll expect to see you in the next lectures. Take care until then. Bye.